Good afternoon, everybody. In this lecture, we're going to talk about seismic source characterization and basically where we get the various parameters that we use to represent seismic sources or faults in our seismic hazard analysis. This picture here shows a couple of geology students that are learning how to trench a fault. So in the previous lectures, we've discussed some of the most basic and important concepts related to probabilistic seismic hazard analysis, as well as deterministic seismic hazard analysis. And for your homework assignment that you'll have this week, you will be performing your own PSHA. And you'll see that it's a good learning experience for you. It's going to challenge you, but I think you'll enjoy it. Today, in this lecture, we want to discuss a few of the more advanced concepts related to PSHA as well as DSHA, and really how we apply PSHA in what I call the real world today, or just a consulting world where people are willing to pay you money for this service. So up to this point, we've talked about seismic sources as if they're just known parameters, like you can go to the seismic source tree in the backyard and pick off some parameters and plug them into your model. The truth is that obtaining these parameters is extremely challenging. And in fact, characterizing seismic sources for a PSHA is arguably the most difficult aspect to performing a PSHA. Now, typically, we use specialized engineering geologists or paleoseismologists to develop these seismic source parameters so that we can characterize the seismic sources in our seismic hazard analysis. And the collection of a group of seismic sources and their associated parameters is what we call a seismic source model. Now, these various parameters include magnitude and distances, or magnitudes and their associated probability distributions, locations of the fault so we can compute distances, the geometry of the fault like the dip and the strike, the various segmentation and the recurrence, the magnitude recurrence and the slip rates for each of those various segments. Now, maybe some of you remember the old cartoon called G.I. Joe, and they'd always say, now knowing is half the battle. Well, I'm here to say that in a PSHA, having a good seismic source model is all of the battle. It's definitely all of it, because without a good seismic source model, it doesn't matter how sophisticated or complex your probabilistic calculations are, garbage in always equals garbage out. So how do these engineering geologists and paleoseismologists evaluate seismic sources and develop these various source parameters that comprise a seismic source model? Well, there's different things. One thing they may do is they may evaluate geologic evidence of the various seismic sources. And so this evidence involves what we call like reading the history recorded in the ground and in the geomorphology. They may go and visit the site and try to study and interpret what the fault looks like. They may try to trench the fault, like we saw on the picture on the first slide, and get down and try to interpret and see what the different faulting parameters may look like. They may try to perform superficial reconnaissance of the fault, where they will go and investigate evidences of different slippage. They may try to use different geophysical remote sensing methods to detect where the fault plane is. All these things involve physically studying the fault. And so this is what we call geologic evidence. And it's perhaps and arguably the most reliable type of evidence that these experts can use in evaluating seismic source parameters. The next type of evidence they can use is historical evidence. So historical evidence means just going back and trying to research history to look for any type of indication that seismic activity has occurred in the past in the area, and hopefully from that particular seismic source. So they may look in pre-instrumental sources of evidence, such as newspaper or journal clippings, those kinds of things, to look for any evidence that old earthquakes may have occurred in that area. They may also look at instrumental evidence. So instrumental evidence has been collected since the 1930s. This is actual recordings of ground motions from real earthquakes on that potential source. This type of evidence is extremely valuable because it tells us a lot about how ground motions actually happen on that particular seismic source. And if we've been recording data for long enough, and if the fault is or the source is active enough, we may be able to begin to infer things like recurrence and those kinds of things, though that's unlikely because most fault recurrence is in the order of hundreds of years, and we've only been recording earthquakes for 80, 90 years or so. So I expect that instrumental evidence is going to become a lot more used and a lot more reliable with time as we continue to record more and more earthquakes. And then, of course, the academic literature review. All of these engineering geologists and paleoseismologists, no matter how good they are, they all started somewhere, and all that was usually in graduate school. A lot of experts will go to the graduate school theses and dissertations to look for studies or seismic source parameters or indications of seismic activity on different seismic sources. All of these things can be very, very valuable, but you have to be a little bit careful because you can talk to any graduate student and they'll be the first to tell you that their work might not be the most reliable. Most graduate students are just trying to make their way through school and check all the necessary boxes. And the peer review for these theses and dissertations is not always the most rigorous. So you have to keep that in mind if you're going to rely on academic theses and dissertations to get these type of seismic source parameters. So what do we do if we want to perform a PSHA and we need a seismic source model? Where do we go? How do we get a seismic source model? There's a few things we can do. We can hire an expert to build us our own site-specific seismic source model, and this is a very reliable and a great way to go. They can get you precisely the data and the type of model that you need. The downside to this approach, of course, is that it's very expensive. These experts do not charge a minimum fee. I mean, it's quite pricey to do this type of study. Another thing we can do is we can rely on publicly available seismic source data and then seismic source models, like those developed by the U.S. Geological Survey. This type of data is extremely valuable. The downside of the data is that its resolution is kind of poor. And we can't fault the USGS for this because their task is to try to build a seismic source model that can be used for any number of applications in any location in the United States. That's a tall order. And so they've done a remarkable job with the seismic source models that they've developed. But when it comes right down to it, there are many quaternary faults, for instance, that do not appear as individual sources in the USGS seismic source model. Instead, they lump them in as background seismicity. Only the most active faults generally get their own seismic source characterization in the publicly available USGS seismic source model. Now, this model is typically updated every 6 years. The first model was in 1996, and then updated again in 2002, 2008, and most recently in 2014. So a simple Google search on USGS probabilistic seismic hazard maps and seismic source model should give you a whole bunch of information and tools and websites necessary to take advantage of this great resource. Finally, one thing you can do is if you work for a firm that has done a lot of site-specific PSHA work in the past, then you can go ahead and search your own archives and look to see if a seismic source model has been built in the past for a location near the site where you're currently working. You know, the upside to this is that it is a site-specific study, and so the data can be pretty good. The downside is that the data may be outdated depending on how old the study is. So, of all of these three different options, which one do we rely most upon? Typically, it's number 2, as you can guess. The vast majority of engineering design in the United States today relies upon the probabilistic ground motion calculations from the USGS, which of course are based on their own seismic source model. You know, going back to the USGS, they've done an amazing amount of work to characterize even individual seismic sources, and they have a large database that they keep on the internet called the Quaternary Fault and Fold Database. This is very helpful. Now, they may not, or well, they do not have probabilistic seismic source parameters included on this. They don't have recurrence law parameters in there like Gutenberg-Richter coefficients, A and B coefficients. But they do have some very helpful geometry information, so fault length, the depth, the dip angle, the strike, those kinds of things. Those are all included in this database, and so a link is shown here. An example of the type of data we can get from the USGS probabilistic seismic source model can be found at this website here. And this data that you can get from this website is more like the recurrence law type of data. And so that may be more useful if you want to perform a PSHA. Now this link takes us to the 2008 seismic source model, but we can get, there's other links on the same web page that would take you to the more current 2014 seismic source model database. Now, let's talk a little bit about the uncertainty related to seismic sources. Now, we spent all of last week discussing how PSHA can account for a lot of different uncertainties. Now, you're going to remember some of those uncertainties, of course, are going to be how big is the earthquake going to be? Where is the earthquake going to occur? How strong or intense will the shaking be at my site from that particular earthquake? And when or what is the likelihood that earthquake will occur in a given amount of time? So those are the uncertainties that PSHA attempts to account for. But the thing we have to remember is that those uncertainties, or all of the, that PSHA that we spoke about, those all assumed that we were 100% confident in characterizing our seismic sources. So, that's a problem, because if I go and let's say that I have, paleoseismologist number 1, and he says that my seismic sources are, like this, and then you've got another paleoseismologist number 2 who says, I disagree. What do we do? Because what it boils down to is we just simply don't always know which seismic source parameters are most reliable. In addition to that, we may not know, for instance, which attenuation relationships are going to produce the best prediction of shaking at our site. All of these things are very challenging, and how do we account for uncertainties in those types of things? And so let's talk about some strategies we can apply to deal with that type of uncertainty. But before we do that, let's zoom out and let's just talk about uncertainty in general from a bird's eye view. Uncertainty in general can be divided into two general categories. The first category is what we call aleatory uncertainty. And aleatory uncertainty deals with randomness in nature. It just deals with our inherent ability to predict all the things that nature can possibly do. So think of this as just the random scatter that's in the data set. This would be things like earthquake magnitude, or the location of where the earthquake might be, or the intensity of the ground motion at our particular site. All of those things are based off of uncertain data. If we make a prediction, it's coming from some prediction model based on scattered data, a data cloud, in other words. So there's no way we can escape aleatory variability. It's always going to be there. And the best thing we can do is just try to wrap our arms around how much fuzziness exists in the data and then try to account for it. Excuse me. The second type of uncertainty is called epistemic uncertainty. Now, epistemic uncertainty is not inherent. Epistemic uncertainty deals with our lack of understanding in the moment. It's our ability, or I should say, our inability to adequately and accurately characterize some aspect of the system, or our ability to predict the outcomes of some event. Epistemic uncertainty inherently then can be reduced or even eliminated if we could just collect all of the data associated with it and develop a true and reliable predictive model, or just develop a new theory that can explain everything with 100% confidence. So epistemic uncertainty is something that we can eliminate with more data, or at least reduce. Aleatory uncertainty is always going to be there no matter how much data we collect. So how do we deal with these various types of uncertainties? Well, aleatory uncertainty, it may sound scary, but the reality is this one's really easy to handle. All we're going to do is we're going to integrate through every possible value of our input, and then we're going to multiply the results by the probability density function associated with that assumed input value. So we're just going to iterate through every possible input and weight the results accordingly to their relative likelihoods. And that's done automatically for us in the PSHA. I mean, that is what the PSHA is. It's just an integral iterating through all of this aleatory uncertainty. Now, epistemic uncertainty is a little more challenging, and we typically will deal with it in earthquake engineering using what are called logic trees. So a logic tree is something that deals with all the possible plausible scenarios that could model our system. And if there's different possibilities, then each possibility then defines a new branch in our logic tree. And for any single level or any single row of branches in our logic tree, like say attenuation model, so in this example, let's say to model the ground motions at my particular site, I want to rely upon 2 attenuation models. And the other ones I don't care about. So I have a Campbell model and a Joyner-Bohr model. Each branch or each level of my logic tree, the probabilities assigned to each branch need to sum up to a value of 1. So in this particular level, you see that my branches sum up to 0.5 plus 0.5. They're going to equal 1. Now, for the next branch here, you could see maybe magnitude distribution. I may want to use like a Gutenberg-Richter recurrence law or a characteristic earthquake recurrence law. Either way, each level of my branch has to equal a value of 1. See how that works? So the point is, for every one of these possibilities, we're going to have multiple branches, we're going to have multiple possibilities, and we're going to just work our way down until we run out of scenarios. And the idea is that if I were to take any single path from the very end twig on my logic tree all the way back to the main trunk, that path represents a completely possible, plausible scenario rupture event for my seismic source. And the same with maybe this branch. Each branch has to represent a possible scenario and a possible ground motion. And so all we're going to do by the time we get through, I should say that each one of these branches is essentially its own PSHA. So we're going to perform multiple PSHA analyses, and then we're going to weight each step in the analysis by its corresponding probabilities, so that by the time we get done, we've ended up with just a giant weighted average PSHA. And that, my friends, is the way that we account for epistemic uncertainty in a seismic hazard analysis. Now let's talk a little bit about how we interpret seismic sources from a PSHA. Now, we learned last week that PSHAs represent a huge probabilistic summation or conglomeration from different individual seismic sources. Now, let me ask, is it possible for us to use the PSHA to infer the amount of risk or hazard associated with each seismic source? And the short answer is, of course, yes. And the way that we can do it is we can use, for one, seismic hazard curves associated with individual seismic sources. You'll recall from the PSHA lectures that a seismic hazard curve is the product of a PSHA. It's the principal thing that is produced from that analysis. And the seismic hazard curve represents, say you have the intensity measure, like the ground motion parameter on the x-axis, and then you have the mean annual rate of exceedance. On the y-axis, and what we get then is a curve that looks like this, so that for any given intensity measure, there's going to be a corresponding hazard value or a mean annual rate of exceeding that hazard value. So we can look at that for individual seismic sources, or we can also look at a second option is what's called a deaggregation plot. That's hard to explain right here. It'll be easier for me to just show you when we get to that point. First, let's talk a little bit about the seismic hazard curves for the various sources. I'm showing here a plot that I pulled out of my PhD dissertation from a few years ago, where I was doing a PSHA analysis for a site located in Costa Rica. Now, the PSHA analyzed every single seismic source with its corresponding range of possible magnitudes, range of possible source-to-site distances, or in other words, where the earthquake was going to originate from on the fault, and computed then the likelihood of exceeding different ground motion levels from that seismic source. So on the x-axis here, I have peak ground acceleration, and then of course this is my lambda, my annual rate of exceedance. And you can see that I have multiple seismic sources that the analysis is giving me. Now, one thing that's really interesting that we could do is, for instance, let's take this the Nicaragua Highland and Shelf source, and I'm trying to trace it down here, and you can kind of follow the red line as it moves. That's that guy right there. And then let's go ahead and also look at, let's see, what's another good one we could look at? Maybe the Limon Fault. That's a good one. So here's the Limon Fault. It runs right through here and crosses and comes down this way. Now, I could look at this and say, Let's take a really small ground motion like 0.01 G, like 1% G. That's something that's really small. Which source is much more likely to produce that ground motion? Well, we'd look at this and we'd say, well, the Limon Fault is giving us, that mean annual likelihood, and the Nicaragua Highland and Shelf is giving us, this mean annual likelihood. And so because the Nicaragua Highland and Shelf has a higher likelihood, we would say we're much more likely to exceed the PGA of 0.01 G from an earthquake on the Nicaragua Highland and Shelf source. But what if we changed this and maybe looked at something a little more substantive? Why don't we look at, say, 0.1 G or 10% G? So if we come up here and look at these values, I'm trying to draw a straight line. I'm struggling here. So in this particular case, bringing this straight line over, here's the mean annual rate of exceedance for the Nicaragua Highland and Shelf source, and here's the mean annual rate of exceedance for the Limon Fault. All of a sudden we realize that, oh, there's a higher likelihood that the Limon Fault is going to have an earthquake that will cause me to exceed an acceleration of 0.1 G at my site. And so looking at these different source seismic hazard curves can be a very useful experience, and we can obtain a lot of valuable information from it with regards to which seismic source is contributing to my seismic hazard. Now, if you don't like one thing I should mention too, if I sum up all of these seismic hazard curves, if I just sum them up, I get what's called the total seismic hazard curve, and that's this big red line right here. Now, you may look at that and say, well, that doesn't look right. How could all those curves, if I add them up, equal this curve? It looks like it's too close to the other data. You got to remember that this is a logarithmic scale, and that's why it's the case. Okay, if you're a person like me, though, looking at these seismic hazard curves can be a little challenging and hard to interpret something useful. And that's why I prefer to look at what are called the aggregation plots. You'll recall that a seismic hazard curve is comprised of different points that we compute from a PSHA. A PSHA is going to compute a single point on a seismic hazard curve. That's where we get the probability that, y is greater than y star, given all the different inputs. So if that is y star, then the likelihood is going to be related to that probability of exceedance. For each one then of those PSHA points, if I just focus on one of those points, so one of those return periods or likelihood levels, you'll recall that this likelihood is actually a summation of a whole bunch of different possibility or different scenario earthquakes with a whole range of magnitude and a whole range of distance. And so for each combination of magnitude and distance, I could have a whole bunch of different scenario events. And so each combination essentially, or each grid, and what do I mean by grid? Well, I mean each one of these little rows for magnitude, each of these magnitude bins and each of these distance bins is going to represent a scenario earthquake that we evaluated in our PSHA. So each one of those bins is going to have a % contribution to our seismic hazard at that return period. So all a deaggregation plot is breaking down this point back into its individual contribution in terms of magnitude and distance. I should label this contribution in terms of percent. That's this axis here. So these plots can be really useful because for a given return period, it can tell us what the mean magnitude and distance combination, or I mean, basically think of this as the mean scenario event for this one return period. What that means is, this whole plot here represents literally hundreds of scenario events. If I had to represent all of those events with a single scenario, it would be the mean. And so that's what it provides us. And for instance, we can get that right here from this line. We can see the mean distance, we can see the mean magnitude, and then even the mean how many standard deviations away from the median computed ground motion we are. The other thing we can get from a deaggregation plot is the modal magnitude and distance, and this represents the single largest contributing scenario. So in this particular case, it would correspond to that column right there, which is, or we could look at it here on our table that the USGS provides us, and that would be a magnitude 6.64 event occurring 4 kilometers away from our site. So the modal is the largest bin on our deaggregation plot. Deaggregations are useful because they help us see the relative contributions from different seismic sources. For instance, this deaggregation plot I'm showing here is a deaggregation I ran for a location, this location right here, which is the married student housing at the University of Washington where I was a graduate student. I just ran this for fun one day because I wanted to see what the seismic hazard was at my apartment. And what we end up seeing, if you look closely at this deaggregation plot, we can see 3 distinct groupings of the data. And each of these 3 distinct groupings actually represents different seismic sources. For instance, this grouping represents the Seattle Fault. They contribute the largest amount of seismic hazard for my apartment in Seattle. And this second group here is the intraplate subduction zone events from Cascadia subduction zone. These very large magnitude events, magnitude 9, magnitude 8.5 events, but that are occurring a large distance away from my site. These are the interplate subduction zone events, or the, sometimes they're called megathrust earthquakes. So you can see which seismic source is contributing the largest amount to my particular site. So there's a lot more we could discuss about deaggregation plots, but what we've said here suffices to get you started, and hopefully you can see that these are some very useful tools. So let's start to wrap things up with regards to seismic hazard analysis. We've discussed both a PSHA and a DSHA over the last few lectures. I always like to ask my students, what do you think? Which one of these do you think is better, is more useful? And, almost nobody raises their hand for DSHA. They always say, no, that's too old school. About a half of the class will raise their hands for PSHA. Well, because my opinion is the only one that matters with regards to this class, at least I'm the one administering the tests, I say that neither is better, and that each of these different approaches has its own useful applications and is used and governs in different situations. So, even building code today, if you try to perform your own site-specific seismic hazard analysis, a building code is going to tell you that you need to do both a DSHA and a PSHA. Because really, only after you compare the results from each of these two analyses can you make an informed decision regarding which ground motion is going to govern your design. Why is that? Well, because most building codes today allow you to select the lesser of the probabilistic and the deterministic ground motions from a PSHA and a DSHA. So you need to perform both so you know which one is smaller. And I need to address why the code allows you to pick the lesser of the two. And it boils down to this, really. If I have a site with seismic sources around it, let's say that each of these seismic sources has a pretty high recurrence rate. Let's say that the return period on average is about 100 years. So, I mean, these would be, not unlike faults located in portions of California, like Northern California or portions of Los Angeles. If I start doing a PSHA, I'm going to evaluate the likelihood of an earthquake occurring on that fault, and the likelihood of an earthquake occurring on that fault, and a likelihood of the earthquake occurring on that fault. And because there's so many faults and all of them have a relatively rapid recurrence interval for earthquakes on them, I'm going to start computing the probability or the likelihood that I could have multiple earthquakes contributing at the same time. And of course, that's bad. We don't want that, because what essentially that is saying is, one earthquake's not bad enough. Let's go ahead and evaluate the likelihood of multiple earthquakes happening simultaneously. Nobody wants to design their building for that. So in these high seismicity areas, what we may say is, okay, let's just evaluate an earthquake on that fault individually, an earthquake on that fault individually, and an earthquake on this fault individually, and let's compare it to the PSHA results. And I'm going to take the largest scenario earthquake from these different sources, and I'm going to compare it to the PSHA. If the PSHA tells me or gives me a ground motion larger than any of my single sources, then I'm not going to believe it. I'm going to know that it's giving me it's adding in the possibility of multiple earthquakes happening simultaneously. Instead, I'm going to rely then on a DSHA for design. If, however, I'm in a place where, like a low or a moderate seismicity area, where, say, this distance from my source to my site might be short, and say that this fault right here has a very long recurrence interval, like let's say, maybe 1,800 years or something like that, then the probabilistic is going to give me a more realistic or a more reasonable answer for what I might expect in the lifetime of my particular structure. And if I rely on a deterministic analysis, the deterministic analysis is going to make the assumption that, yes, this fault is going to go. It's going to be the one that produces the earthquake. And that may be too conservative of an assumption for my particular site. So here's the deal. PSHA is going to govern for the majority of cases of seismic hazard in not only the U.S. but throughout the world, particularly in regions of low to moderate seismicity. However, a DSHA, a deterministic seismic hazard analysis, will give me lesser ground motions if I apply them in areas of high seismicity, particularly in areas where all of the seismic sources have a pretty frequent recurrence interval between earthquake events. So DSHA is going to be used, therefore, as an upper bound for the seismic hazard. And most often in areas of seismicity, or if I'm designing a critical structure, is it going to govern. So wrapping it up, if I'm a consultant and I'm hired to perform a PSHA, my final geotechnical report needs to contain a few things of critical importance. If I was reviewing a PSHA report and any of these things were missing, you better believe I'd have my red pen out and I'd be marking things up and I would be making complaints to the client. It needs to have a section that talks about the regional and the historical seismicity or earthquake activity in near the site. It needs to describe, or in the minimum at least reference, the seismic source model that the PSHA is using with its associated logic tree. In my own consulting, I almost always relied on the USGS seismic source model and its logic tree, so that was easy. All I had to do was reference it. If you build your own seismic source model or have someone do it for you, then you need to include this information in your report, likely in an appendix, and believe me, this stuff can be hundreds of pages in length. We need to provide descriptions of the attenuation relationships that were used and how they were weighted. We need to plot and show the seismic hazard curves that were produced from our PSHA. We need to show the uniform hazard response spectra for return periods of interest. We'll talk a little bit about this in a couple of lectures. We need to also show the deaggregation results from the return periods of interest from the seismic hazard curve. And finally, we need to be sure to provide an interpretation of what all of this stuff means and to boil it down and make it something that is very understandable and easy for the client to interpret, so they cannot make a mistake or misunderstand what we're trying to say. So that's the lecture today, folks. I appreciate your attention. I look forward to seeing you on the next lecture, and have a wonderful day.